All right, now let's talk about characteristics of power functions. So, shown to the right here, we have the graphs of f of x equals x squared in purple, f of x equals x to the fourth in green, and f of x equals x to the sixth power in blue. Notice that all of these graphs have a fairly similar shape. They're all very similar to the quadratic toolkit function. But as the power increases in these functions, these graphs flatten somewhat near the origin and become steeper away from the origin. Also, these are even whole number powers. So maybe we'll take a note of these being even whole number powers. Right, I have powers of 2, 4, and 6. Let's see, as power increases, the graphs flatten near the origin. Because notice here that, like, for instance, f of x equals x to the sixth is very flat near the origin, where f of x equals x squared is not very flat near the origin at all. And these become steeper away from the origin. Notice how f of x equals x to the sixth is growing the fastest, right? It's becoming the steepest, the soonest. So to describe this behavior, to describe the behavior of these graphs, rather, as we let our numbers become larger and larger, we're going to use our idea of infinity. If I say something like x approaches infinity, which can be symbolically represented as, let's see, I'll just say equals x and then this arrow and then the infinity symbol. In this case, I'm describing a behavior. I'm saying here that x is getting large in the positive direction. Or that I'm moving far, 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 far to the right on this graph. With these even power functions, as my x becomes large in either the positive or negative direction, notice that my output values are becoming very large, right? As I go far out to either the left or the right, these graphs are shooting up very quickly, right? So let me write that. Let's see. For these even power functions, as x becomes large, in either the positive or negative direction, the output values become very large positive numbers, right? These graphs are only going upwards as I go to the left and to the right. Oh, I didn't mean to show this graph yet. I'll move this down a little bit. So I could describe this by saying that as x approaches positive or negative infinity, the f of x values approach positive infinity. This is really just another way of wording this last paragraph. In symbolic form, I could write this same thing as saying that as x approaches positive or negative infinity, f of x approaches positive infinity. Now let's look at the whole number odd powers. Here I have the graphs of f of x equals x cubed, f of x equals x to the fifth, and f of x equals x to the seventh. These are all odd whole number powers. Notice that all of these look similar to the cubic toolkit function, but once again, as the power increases, the graphs flatten near the origin and become steeper away from the origin. So notice that, for instance, the graph of f of x equals x to the seventh is the steepest graph, and f of x equals x cubed is the least steep graph, or I guess you could say the most gradually growing graph. For these odd power functions, as x approaches negative infinity, in other words, as we're going to the far left of this graph, f of x approaches negative infinity. In other words, as I go to the far left, the graphs are going down. Similarly, as x approaches positive infinity, there we go. So in other words, as these graphs are going to the far right, f of x approaches positive infinity. In other words, as these graphs are going to the right, they're also going upwards. Symbolically, I would write these two things as, as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches positive infinity. This brings me to this idea of long run behavior. The behavior of the graph of a function as the input takes on large negative values that is as x approaches negative infinity and large positive values, that is x approaches positive infinity, is referred to as the long run behavior of the function. This is sometimes also called end behavior. End behavior is the term that I have always heard and used personally. So let's look at a few examples. Describe the long run behavior or the end behavior of the graph of f of x equals x to the 8th. So this is a whole number, even power, so I would expect this to behave somewhat like the quadratic function. So I would expect that as my input gets large in the positive or negative direction, that my output is going to grow without bound in the positive direction. In other words, I would expect that this function behaves in the manner such that as x approaches positive or negative infinity, f of x approaches positive infinity. If you wanted to write this out on two separate lines, you could. We could instead say as x approaches negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches positive infinity. For these even ones, you can also combine them though. Let's also describe the long run behavior of f of x equals negative x to the 9th. So let's note here that this has a whole odd power. So I expect this to behave somewhat like the cubic function. However, notice that this negative sign in front causes a vertical reflection. So this means that as my inputs grow positive, my outputs are going to become negative. They're going to grow large in the negative direction. And as my inputs grow large in the negative direction, my outputs are going to grow large in the positive direction. So we see that it's going to be a vertical reflection of these graphs here, right? So instead of behaving in this manner, as I go far to the left, the graph will go up, and as I go far to the right, the graph will go down due to that vertical reflection. In other words, roughly, the graph will look something like this, the shape of it at least. So this is going to behave such that as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches negative infinity. And let's look at one more. Long run behavior of f of x equals negative x to the fourth. This has a whole even power. Notice that it has a negative sign in front, which is going to cause a vertical reflection. Meaning instead of being like this, instead of being concave up like a typical kind of quadratic shaped graph, it's going to look like this. It's going to be concave down. So as x approaches negative infinity, f of x is also going to approach negative infinity. And as x approaches positive infinity, f of x is going to approach negative infinity. All right, and that's it for long run behavior. I'm going to make another one on polynomials next.